chunk of this clip going through the naming, the structure and the shape of alkenes. I'm just going to go through those particular areas and not cover isomerism or reactions. So let's start by drawing out alkene bonds. So if we look at the simplest alkene, ethene, the carbon chain length dictates the first part of the name. So the eth part of the name is because you've got two carbons. The ene part of the name comes from the fact that there is a double bond between those two carbons. So if we look at propene, for example, your fully displayed formula shows all the bonds. The partially displayed formula has the methyl group on the right hand side written as CH3, and in all cases the C double bond C is clearly shown. So you can see the structural formula there with C double bond C in it, and also the skeletal formula with the double bond indicated. Looking at naming alkenes, it's quite straightforward. Let's look at butene. So I've called it but1ene because the carbon-carbon double bond is on the left-hand side, so I'm numbering my carbons from left to right. So that gives me something called a locant number, which is the location of any functional groups or bonds of interest. But2ene is the double bond starting on carbon number 2, and you could also count it from the right-hand side because it's a symmetrical alkene. With bond conductivity, it's quite important to make sure that the carbons are shown bonded to each other in the way they are, rather than writing CH3 where it looks like the hydrogen is bonded to the carbon instead. So I write H3C on the bottom left there. Alkenes can also be in ring structures. We call these alicyclic, and they have a carbon-carbon double bond, and you can draw it as displayed or as skeletal, as you can see here. So diene is a compound that has two carbon-carbon double bonds in different places of the molecule. Let's move this out of the way there. And this compound would be called buta-1,3-diene because the double bonds start at carbon atoms 1 and 3. And like we said a moment ago, you could also count it the other way around because one of the carbon-carbon double bonds is at the end in both ends in this particular case. So let's look at how the bonding works in alkenes for a few minutes. So a sigma bond is basically a head-on overlap of orbitals that occur between atoms in single covalent bonds. So that takes place in carbon-hydrogen single bonds and also part of the double bond itself. So in addition to the sigma bond, in a double bond you also have something called a pi bond, which is a sideways overlap between p orbitals specifically. Okay, so if we look at the graphic there, you can see that the p orbitals have actually been drawn in, and what happens is they overlap with one another and start to pull the carbons closer together, and the sigma bond remains intact whilst a new pi bond is formed, and that gives rise to the structure we looked at a few minutes ago. So looking at the bond angles in alkenes, carbon-carbon double bond is treated as a single region of electron density. So with that in mind, each carbon atom will have 3 bond pairs and no lone pairs. And therefore the bond angle will be 120 degrees. And as a result, you'll get trigonal planar in shape. Now when you get slightly more complicated alkenes, when you have more than one type of bond angle, you need to make sure that they take place at the same time, and the shapes are considered as next door to each other. So if I draw that out slightly corrected, you've got the carbon-carbon double bond and 120 degree bond angle, plus you've also got the tetrahedral arrangement around the carbon and the methyl group, which is 109.5 degrees. So let's look at a short exam question. They want the value of the bond angle A in propane and the bond angle B in propene. So that's just an application of what we looked at a few seconds ago. So no surprises here. You're going to have 109.5 in the carbon around propane and 120 in the carbon-carbon around the CC double bond in propene. Okay, so hopefully this has been a useful clip, a quick introduction to alkenes and their structure. Thanks for listening. Until next time, see you soon.